want to look at expected value. When we're looking at expected value, we're wanting to look at what's our expected outcome. In other words, what do we expect to get? Do we expect to get a profit? Do we expect to lose money? So when we look at something, let's look at if a player rolls a die and receives $1 for each dot on the face she rolls, the amount of money won on a roll can be represented by the value or by the variable x. So let's just take and say that this is x, and then we're going to look at the probability of x. What's the probability that she gets that amount? So if we roll a die and she receives $1 for each dot on the face that she rolls. Okay, so we roll a die. So if she rolls a 1, she gets $1. If she rolls a 2, she's going to get $2. Rolls a 3, she's going to get $3. Rolls a 4, rolls a 5, rolls a 6. So what's the probability of her getting $1? Well, that's the probability of her rolling a 1. Well, that's 1 out of 6. And so each of these have a 1 out of 6 chance of getting this. So in this particular case, the player has the same probability to receive each amount of money or is expected to receive. Now, expected value is used to predict the average result of an experiment when it's repeated many times. It's not used to predict the outcome of a single experiment. So in other words, just one game is not going to tell us, yes, you're going to win this amount on one game. It's if you play 100 or 1,000 times type of thing. When payoffs are involved and expected value minus the cost to play the game of chance is 0, the game is a fair game. Previously, a fair game was defined as a game in which each player has an equal chance of winning. If there are 2 players and each has the same probability of winning, a given number of dollars for the other, it follows that the expected value minus the cost to play, net winnings, for each player is 0. So in other words, for it to be fair, we want the overall expected value to be 0. Now, how we calculate the expected value is we take the amount of winnings times its probability. Amount of winnings times the probability. Okay? So, in other words, how much are we going to acquire times the probability, and then at the end, we'll subtract out the cost of it to see, do we have a fair game? So let's look at example 8. You play a game where you bet $1. So let's just come over here and look at the cost is $1. If you win the game, you win $20. If you lose the game, you lose your $1. So if we win, we get $20. If we lose, basically, we don't win anything. We're going to lose our $1, okay? Probability of winning the game is 0.08. So how can we find the probability of losing the game? Well, think about this game. There's only 2 outcomes. We either win or we lose. What do probabilities all have to add up to be? The sum of the probabilities must add up to be 1. So 1 minus 0.08 is going to be a 0.92. That's the probability of losing. So I'm going to take how much I win times its probability, and then I'm going to take how much I'm going to lose times its probability. Obviously, this is going to be 0. 20 times 0.08 is going to be $1.60. And then I'm going to take out my cost, so $1.60 minus the cost. So 160 minus $1 is going to be 60 cents. So on average, and since this is a positive, I'm going to gain 60 cents. So is this a fair game? No, because we don't have a 0 net winning. In other words, we would have wanted this to be 0 for it to be a fair game. The player wins more of the time in this particular case. Okay? Now, let's look at example 9. Suppose 5 quarters, 5 dimes, 5 nickels, and 10 pennies are in a box. 1 coin is selected at random. What is the expected value of this experiment? So here we need to take the probability of drawing each item. So we have quarters, dimes, nickels, and pennies. So we have 5 quarters, 5 dimes, 5 nickels, and 10 pennies. So that means that there are a total of 25 coins. So the probability of drawing a quarter is 5 out of 25. 5 out of 25, 5 out of 25, and 10 out of 25. So that's the probability of drawing each one of these. Then what I'm going to do is I'm going to multiply each one of these by their value. So a quarter is worth 25 cents. A dime is worth 10 cents. A nickel is worth 5 cents. And a penny is worth 1 cent. And then I will add these up. So 0.25 times 5 divided by 25 is going to be a 0.05. 10 cents times 5 divided by 25 is going to be a 0.02. 5 cents times 5 divided by 25 will be a 0.01. 0.01 divided times 10 divided by 25 would be a 0.004. And if I add that up, that's going to be a 0.084. So we're looking at approximately, not $8. We're looking at approximately 8 cents is our expected value on this particular experiment. Now, are we going to get exactly 8 cents? No, because we can't get 8 cents on any of these. That's if we, overall, if we take the average on about 1,000 times we do this.